Okay. Okay. We are going to. I'm going to give you a short talk about the cryogenic facility at INPE for LIGO Voyager IND. Our group working with this cryogenic research is this one. I hope more students, new students, four are here. New students will join us. They are still doing coursework or trying to finish master thesis. Okay, well, this is the logos of the LIGO scientific collaboration. And so our institute is, this is the International Institute of Physics, and our logo is this one, okay, INPE. It stands for National Institute for Space Research. So we have 2 sites in South America. This is here in Natal, and this is close to São Paulo City. It's about 80 kilometers, 85 kilometers from São Paulo City. It's São José dos Campos. Okay? It's the only 2 groups in Latin America, unfortunately, so far. We hope this scenario changes in the near future. Okay, this one, for example, is almost Mexico. It's the where Volker and Mario came. Yeah, this one, right, Volker? Is it correct? Is it on the tip of the Texas state? The south tip. Okay. We are trying to work with LIGO Voyager because LIGO Voyager will have sensitivity better than A+, okay? And of course, as advanced LIGO, okay? In the middle frequencies and also low frequencies. We have a tradition in our institute for doing cryogenics because there is a place for satellite assembling. So when we entered this business, of course we had a background from bar and sphere detectors, cryogenics, liquid helium cryogenics from them, but we need some facility to do our tests. And initially we used this one that was used for satellites, okay? And it's, well, an old facility there. They have a bigger one now. And so we did our initial tests there, okay? This was our experiment. We put a heat source inside some cylindrical shells, and a set of cylindrical shells, 5 cylindrical shells, okay? And we circulate liquid nitrogen through piping here, those aluminum shells, and we study the cool down of this system, okay? Using their temperature collecting system, which they have already, okay? Now, we have our own vacuum cryogenic chamber. This is is 4 meter high, 2 meter in diameter, and we have liquid nitrogen piping circulating around it, so create a cold environment, 1.5 meter diameter and 1.5 meter in height. This space, everything that we put inside this space is cooled to liquid nitrogen temperature, or close to it. Okay. And it's actually 4.5 meter high. Okay, and so this is the picture when it came. the cylindrical shell circulating the piping of liquid nitrogen. So those are valves that we control the many fluxes and things connecting inside. There is a liquid nitrogen reservoir. We can give a pressure in the reservoir and force liquid nitrogen to go from below, and we can pump out this liquid nitrogen. So instead of 77 K, it can be at 65 K, almost 63 K, and we pump and we circulate this subcooled liquid nitrogen in those pipings. Okay, this is before the super insulation was installed. We test this experiment of vibration isolation system that we built, because it also works for at room temperature, of course. So this is the schematic of the circulating piping, and this is after the liquid, super insulation was installed. Okay. We did this experiment using the test mass with the size of advanced LIGO test mass, but made of aluminum and hollow aluminum. Okay, and we put a heat source inside, and this is the prototype of the test mass, and this is the heat shielding. Okay, and so this is, and we have a tank, a 6,000 liter external tank that can provide us with an infinity amount of liquid nitrogen, because we can refill this tank during the run. So here you see 10-hour experiment. No, I'm sorry, a continuous 4-day experiment. Okay, yes, of course. Continue 4-day experiment, and we have longer experiments too. Takes a week. Continuous 7-day experiment. We also installed a heat switch, and this is a schematic view of how it works. You have a rod here, a manual rod that you can rotate, and that's how you have it. Here is the actual thing, and this is the rod, and you can rotate, and you also can put some weight and keep pressuring with some non-weight. This is the heat switch, and those rods go inside the liquid nitrogen reservoir up to the bottom, and we have thermal sensors, strain gauges around the path, so we know the temperature of this thermal heat switch. And so this is the thing. This is the liquid nitrogen reservoir, and this is the super insulation. And this is a top view. The liquid nitrogen reservoir is down there. Is a view from the top. And this is the run. Was a 7-day run. Okay. Actually, we did many runs, one after the other, doing different things, just using the heat switch, thermal switch plus conduction, metal conduction, and by radiation. So thermal switch only, heat switch plus radiation. And this one was with gas, too, all three processes. And this is a picture when it was cold. Because there is no thermal, because there is no double wall vacuum, so the outside chamber became sweat. I mean, water condensate on it. But it doesn't really bother us. Okay, this is another run. And okay, and this is, I'm going to end with a little experiment that we did recently using a small cryostat. We have also a few cryostats, smaller ones, that we can do measurements. This is a cryostat that we did use a silicon sample, small silicon sample, to measure its emissivity. So we put the silicon sample here, and we fill up these with liquid nitrogen up to almost the top, and then we immerse these immediately. So suddenly, all these walls became at 77, actually 82 Kelvin, according to the thermometer. Because there was always some flux going down through the metals, this metal pipe. And so we immerse immediately everything, and so the walls is the red curve, went down in about 4 minutes, 4, 5, 6 minutes. And then most of the time, it was already at standard, a constant temperature of around 82 Kelvin. Okay? The pressure was pretty good. This is in millibar. This one, 6 × 10⁻⁸ millibar. So the conduction through the gas was negligible. And the only process of cooling down was radiation, because we did a calculation with the wires, including the wires for the thermometers, and they were negligible. At least 100 times the conductivity through the heat would be 100, 1 part in 100 only. The heat was being transferred through the wires. Okay, and this is when we warm up the experiment. We also follow the curve of the warming up. And it's funny because the intuition is that you also will have a slow warming up, but it's completely different. It's an asymmetrical problem, because when you are cooling down, the only heat source is the sample. And when you are warming up, the whole, all the walls are hot, almost 300 K. So the sample receives this large amount of heat coming from from everywhere from the wall. So the heat balance here, the heat that is involved in this cool down is completely much smaller than the heat is involved in this warm up. The flux of heat. This is the sample, the silicon sample. Was 7 centimeters long, 3 centimeters in wide, and about 1 centimeter in thickness. Okay, and the wires were titanium, aluminum, vanadium wires. Though this is the same material that suspended all the bars. The bars had these materials. It's a very tough material, very reliable for cryogenics, and is also low conductivity metal. Okay. And this is the sensors, the heat thermocouples. We use two, one here and one there. And also the wires for these thermocouples were very thin. So this is the result of the emissivity already calculated as a function of temperature. So you see that the thing, this is not really physical. It's more because the, I don't have here, but the temperature, because the thermocouples are digital, so they jump, they keep jumping the temperature. They change when they are cooling down, and they go back again. So they keep doing. So actually these curves here, I mean, this curve here is a mess. If you give a zoom, it goes back and forth and has nothing, no information there. It's just the statistics of thermocouple changing, reading, because it doesn't have too many decimal places. Okay. So we fit this curve. It gives this value. This was a first run that we did. We did a second run, and we got a slightly different result. But you see that that thing is not real, because in another run it has another shape. Okay. So what is really meaningful is the fitting. Yes? No, this is not this is just cooling down. So the black body radiation is moving. Every temperature here, the black body radiation is at a peak of some frequency. When the piece is getting colder, the black body radiation is moving towards the larger, longer wavelength. Okay. But this is already the integrated effect. Yes, of course. This is not emissivity as a function of frequency. It's the overall emissivity for the actual cooling process. Oh, yes. Okay. Now, we did, one funny thing is that this is experiment 1, experiment 2 plotted, one on the top of the other. And this is using the average result from the 2 runs. We got this emissivity equation, and we did use Python and calculate the cooling down, and it fit completely on the top of the 2 runs. This is a simulation in red, and a calculate value for 0.5. So and so after the same time, they meet here at 125 Kelvin. So this is one funny thing. if you use emissivity, constant emissivity of 0.5, you get the same time of cooling up to 125. So it means that actually this emissivity that is running from 0.7 to 0.4 actually is equivalent to a constant emissivity at 0.5, roughly, okay? It's not at the average of 0.4 and 0.7 because the sample spends more time at lower temperatures. So this curve here spends more time. So it's just a funny result. I mean, interesting result. So using this equation, now we can calculate for LIGO Voyager. This is one of the test masses. This is the input test mass. This is the compensation plate, inner shield, the outer shield, and this is the piping, the tube, external room temperature. And okay, and so we did this calculation. This is with the laser on and with the laser off, okay? And this is for painting the barrel, of the mirror with some high emissivity painting, 0.95. You can do even closer to 1, but just using 0.95, and we get these red and blue curves. The blue curve is with the laser off, and the red one with the laser on. And using the results that we got from our experiment, our measurements, we get the purple and the black curve. Well, there is no reason to cool the experiment, the test mass with the laser on. So we just forget about those curves of laser on. So the interesting curve is the black one, and gives you a result of a week for cooling down the silicon, 200 kilogram silicon test mass up to 125 Kelvin, okay? 1 week is reasonable because pumping down takes 2 weeks. Almost, actually more than 2 weeks, but so if the pumping down is also taking 2 weeks, so 1 week for the cooling down, it's reasonable, okay? And also, it may be not a good idea to use gas, because if you use gas, you are delaying your pumping down, okay? So you are going to get also problems of water condensation, okay? And so our proposal is just use radiation as cooling down, no heat switch or gas exchange gas. Okay. Okay.
Yeah, so we can ask questions, we can start a cryogenics discussion, thermal noise